All right, so we are talking about the light unit for physics now. We're going to be talking about the refraction and the double and single slit experiments and their repercussions. All right, so this time around, the learning goal for today is learn the structure of light in modern science as it is, and use some of the terms to describe it, right? So we're going to use some sort of historical background here in order to cover, sort of the progression of the thoughts of light in humanity here, right? So we'll go ahead and go way back to start with. We'll talk about Pythagoras, right? Now, uh, these are different opinions that famous mathematicians and scientists had throughout the years. And we'll kind of get to the more modern versions of this as well, such that by the end of this unit, you're going to be kind of talking about the idea that, some of these people were correct and others were not, all right? And so Pythagoreans here, right? So one opinion held that the eye actually sends out rays to objects, and that these rays give the viewer information about color and shape, right? And so that was the Pythagoreans' original thoughts. It's like, what was the idea of light? And, it actually came from the eyes, right? Um, and so there's another alternative history. This is from Aristotle here. And basically, Aristotle says that the visual perception suggested that the light occurs because the rays emanate from the perceiver's eyes. After leaving the eyes, these go and they explore the world, right? And they encounter objects, and then they go back, right? Diversely, it's like, well, one, they just kind of come from the eyes and they sort of see stuff, whereas the other one is they actually go through the eyes or from the eyes and then hit stuff and come back. So you have, in a way, a little added bonus of the idea of reflection here of Aristotle. As we all know, light does reflect off of things, and so it was a little bit of an added sort of addition to the current knowledge, or well, I guess what was previously accepted to be the current idea of light. Okay, and then nothing really changed for a long time until this guy. I don't even remember how to say. I don't know how to say this. Huygens or something like that. Huygens, right? Came along and came along with the idea that thinking that light was waves, right, and sort of vibrated up and down, perpendicular to the direction that the light actually traveled, right, and and then basically, so you ended up having these waves that sort of propagated out, right, and well, that was kind of like a bit of a wave theory, right, and then the other guy, Newton, at the time was like, "I don't know, I'm not sure about that." Isaac Newton argued that because they reflected and refracted, right? We'll talk about these characteristics, okay? That it has to be particles, right? Because basically they kind of traveled in straight lines, and particles like little marbles or bits of sand, you could see that they could reflect and refract as well. If you would maybe have like um, a scenario like that, all right. And then of course we had Young that comes along, and his major contribution to light was this famous double slit experiment. Some people say it's the best, one of the best, greatest experiments of all time. Uh, so we will definitely talk extensively about this experiment here. Okay. So that's kind of the idea. It really sort of vastly changed over the course of thousands of years, right? And, I imagine, even still nowadays, light is a little bit mysterious, and we're still learning some stuff about it in physics. All right. So let's go ahead and talk about the idea of this wave light, right? And we'll also talk about the idea of light being a particle, but a little later on, though, we're going to kind of skip straight to Huygens here. We're going to skip Aristotle and Pythagoras because there's really no support for these theories, and we're not going to have any sort of mathematics that supports these guys, right? So in the end, what we're doing is we're going to skip straight to the ones that actually have a mathematical sort of explanation. And Huygens, Huygens had it. And so we'll go ahead and talk about his idea here. So basically, his idea is that, light needs to come from some sort of source, right? And so what we're going to do here is basically talk about what is a wave source. So we could have a point source or a line source in a way, right? And so what we would have is, let me draw this out. Let me get blue here. If I've got a point source, then the light emanates out in a circular fashion from this source. It's actually spherical, right? In a spherical fashion. Okay, and it travels out. I'll try and make one really nice circle there. Okay, so there's our sort of light. And so the light ray actually travels in this direction, okay? And then there will be another one traveling in that direction, another one traveling in that direction. So it would be every direction. That's the direction of the light itself, okay? And what's the idea with these circles, right? These would be considered like, in a way, sort of crests and troughs. So these would be like wave fronts here. So remember what Huygens was saying is that the light vibrates in an up-down fashion. So you can kind of imagine this sort of being like a hilly kind of thing here, where you've got sort of the tops of your hills are these upper bits here, and then you've got the lower bits and here as well, in between each one, right? And so these would be considered wave fronts. So this would be a point source, all right? And then we could have a line source as well, where basically you've got some sort of source that's sort of producing light all at the same time here. And as a result, you get waves that come out in a straight fashion like this, okay? Now, one thing to keep in mind is that this guy, Huygens, conceded the fact that these line sources were actually not lines, right? They were actually a bunch of individual adjacent points, right? And so, for example, if you were to make several individual adjacent point sources, right, then each one would have its own sort of circle like this, right? Then this guy would have its own circle that would be slightly to the left of it. And this guy would have his own circle, which would be slightly to the left of that. And then another one slightly to the left, and another one slightly to the left, and so forth, and so forth, and so forth. And as a result, all of these sort of crests would compound upon one another, and in a way form a straight line crest right here, right? And then as it moved out to here, there would be a new one to replace it back in this area. And so each one of these crests would come out in what would be seemingly a straight line, but in reality, in what this guy's opinion was, that it was that they were just several adjacent point sources. Okay. That's how you get a line source, okay? All right, so that's kind of the idea of waves, right? Now, what we're going to do is we're also going to talk about water and sound, right, in this unit as well, in order to sort of draw an analogous uh, uh, opinion so that we can kind of, say, well, light behaves like water in this fashion, and so therefore it must be a wave. Or light behaves like sound in this fashion, so it must also behave like a sound wave, and so therefore light is a wave. Okay, in essence, or kind of like the idea. It's not that light is a wave. The best mathematical representation of light is a wave structure of mathematics. Okay, and so maybe you could even just say light is a wave at that point. Okay. And so one thing that happens is refraction. Okay. In water, when the depth of water changes, so does the wave velocity. And so what ends up happening is you get this idea of refraction. Okay. And so let's I'm gonna take this and I'm gonna draw like a little side view here. So imagine water coming up, and I've got my water here, and I've got a wave, right? And what ends up happening is the waves, if I change the depth of water, the waves kind of compress a bit, the wavelength, all right? Here, it went from there, pretty big wavelength, to a shorter wavelength, okay? And the idea is that what happens is the velocity with which the water is moving is it changes, okay? And so therefore the wavelength itself ends up changing, okay? So we're going to have to keep that in mind there. So what happens is, in this first bit, the velocity of the wave is pretty big, right? And then over here, your velocity decreases as well. So I'm going to call this wavelength. I'm going to call this wavelength 1, and I'm going to call this guy wavelength 2, right? And by the way, this is a lambda. A lambda, which is the variable for wavelength. And I'm going to call this velocity 1, and I'm going to call that guy velocity 2, right? And one of the things that actually stays the same in this scenario is the frequency of the waves. So frequency 1 and frequency 2 are the same. Now, frequency is the number of waves that pass a certain point in a given time interval, just like regular frequency is, okay? And so if you think about that, that makes sense. Imagine I'm standing or like hovering or whatever here, and I count for 10 seconds and 6 waves go by. And then somebody over here is standing and they count for 10 seconds and 8 waves go by. And well, then you might say, well, wait a minute. If this guy only saw 6 waves go by, and then this guy a little bit down the road saw 8 waves go by, then where did the other waves come from? Okay, because this guy's got a frequency of maybe 6. He's got a continuous frequency of 6 waves per second, let's say, and this guy's got a continuous frequency of 8 waves per second. You'd be saying, well, wait a minute, that means every second, like two brand new waves are generated in between this area and this area. That's impossible. You can't generate brand new waves out of nothing. They have to come from way over here, the source, okay? Otherwise, you would end up having, if you had a source here, then yeah, okay, you could do that. So that's why the frequencies must stay the same. The same goes for the fact that, let's say I had a frequency of like 10 here, and then later on I had a frequency of 5. The question would be, well, where did those other 5 waves go? They just disappear? No. And so, or did they get like, stuck somewhere? No, it doesn't happen that way. So the frequency of the waves stays the same everywhere, okay? But if the wavelength changes, so must the velocity with which it moves, okay? And the formula ends up basically looking like this, right? You know that velocity is wavelength times frequency. We know that velocity is wavelength times frequency, okay? I'm not sure if we studied this formula in this course yet, but I'll explain it. Why? Well, because the units for wavelength are meters, and the units for frequency are cycles per second, right? And so if you look closely at that, that's meters times per second is actually meters per second. And so therefore, your velocity is meters per second, right? And so in the end, if I say like velocity 1, wavelength 1, frequency 1, then I say velocity 2 and wavelength 2 and frequency 2, and if I solve for frequency in both of these formulas, I get velocity 1 over wavelength 1 equals frequency 1. And I get velocity 2 over wavelength 2 equals frequency 2. But we said that it would be impossible for us to lose or gain waves out of nothing. And so therefore the frequency is always the same. And so since frequency 1 is equal to frequency 2, therefore velocity 1 over wavelength 1 is equal to velocity 2 over wavelength 2, okay? And so this is now basically the idea of refraction, all right? So what happens is the ratio of the first velocity and the second wavelength. That's why a larger wavelength has a larger velocity and a smaller wavelength has a smaller velocity. Because, for example, if I had a 4 over 4 here, then I would have to have a 3 over 3 here, because in the end, 4 over 4 is 1, and 3 over 3 is also 1, and so therefore they're equal, okay? They're equal because their frequencies would be equal, all right? So that's the origin of this formula here, okay? Now, oftentimes, you won't see it written like this, but what will happen is in your textbook, they're going to cross multiply this and basically say that V1 over V2 is equal to lambda 1 over lambda 2. So the ratio of the velocities is equal to the ratio of the wavelengths, okay, for refracted water, okay? Well, it turns out with light, a similar phenomenon occurs. And when light not goes from, so it's different. Like it happens with water when it goes from a deep section to a shallow section. This is water here. So this is like a deep ocean. Then all of a sudden it goes shallow and this phenomenon of refraction occurs, right? Well, with light, instead of going from like a deep section to a shallow section, because that doesn't make sense with light, what happens is if it's when the light goes into a different medium, all right? And so that would be called the refraction of light. And I think I have a picture of that. Oh no, my picture, where did it go? Let me pause the video and see if I can grab that picture. All right, so yep, there it is. There's my picture. Okay. So with light, a similar phenomenon occurs when light moves into a different medium. Okay. So let me explain this picture here, right? So we've got some light coming in, and it's coming in actually at an angle as well. Okay. And the angle is also helpful. So it's coming in at an angle here, and then this is a barrier. This is maybe like out here is like air, and in here is like glass. Okay, so when light hits this thing, right, the velocity that it had out here would be maybe considered velocity 1, and the velocity that it has in here would be considered velocity 2, right? And the wavelength that it has out here would be this guy, the wavelength, okay? And the wavelength that it has here would be wavelength 2, all right? And then there's also angles here, right? And so you end up with this geometry, right? So you basically get V1 over V2 is equal to wavelength 1 over wavelength 2. And now it actually is equal to the sine of the first angle and the sine of the second angle, okay? This is oftentimes called the angle of incidence, and this is the angle of refraction. See in my diagram, there's a little I there and a little R there, okay? So this is the refracted wavelength. This is the incidental wavelength. This is the velocity, right? Incidental velocity and the refracted velocity, okay? Now, why does this end up happening, right? Because basically what happens is the light itself travels at different velocities in this stuff, which is air out here, versus this stuff, which would be maybe glass or something. So imagine what's going on here. I've got my light, right? And it's moving fast here, and then it gets into the glass and it moves a little slower, all right? Well, if it does move a little slower over there, then what would happen is you would say, okay, this is let's look at this wavefront here, right? You can see that this wavefront here versus that wavefront there, this guy has been in the slower moving stuff for a little while longer, and so as a result, he doesn't go as far. So as a result, their wavelength ends up compressing as each wavefront starts to enter the glass here, okay? So you can kind of see that these blue lines end up getting tilted back a bit. And if I were to put in more blue lines, it would be kind of like something like this, right? So you could kind of see large wavelengths out there, and small wavelengths over there, right? And it's because the light is moving slower in here, and so their wavelength ends up compressing down. Anyway, here's the equation that dictates all of this, all right? And then there's also another number called n, okay, n, and this one, the 2 is on the top and the 1 is on the bottom. And this is called the index of refraction, and this is a number that's assigned to certain materials, okay? And they basically give a vacuum an index of refraction of 1. So a vacuum where you basically have nothingness, no medium, right? So you've got no air, no glass, no water, right? Nothing is a index of refraction of 1. And then other things like water, right, has an index of refraction of maybe, I think it's like, is it 1.3 if I remember correctly? I have to look in there's a reference manual. It's 1.333, okay? And you'll find this on page 448. If you're doing some practice there, you'll find all of the, not all, but indexes of refraction for several common materials, Okay. All right. So this, by the way, this whole thing is together. This equation here is called Snell's law. It's found on your formula sheet. So now we're going to go ahead and put this into practice. So we're going to calculate the angle light turns as it changes from one substance to another. So we're going to learn how the mathematics of Snell law is used to predict what happens to light as it moves from one substance to another. So here's a question, 3 examples, maybe three examples. When light passes from air into water at an angle of 60 degrees from the normal, what is the angle of refraction, right? The answer is 40.6. So basically, we've got light that passes from air, right? So we've got N1 is air, and N2 is water, right? And the angle of incidence is 60. So theta 1 is 60 degrees. And we're wanting to know the angle of refraction, okay? And so I'm going to go ahead and use my reference on page 448. And I'm going to see that air is 1.00029. Water is 1.333. So I would just basically go and I would grab Snell's law. I would grab this section of Snell's law and I would say that the sine of 1 over the sine of 2 is equal to n of 2 over n sub 1. So I've got the sine of 60 over the sine of theta 2 is equal to n2, which is 1.333 over n1, which is 1.00029, right? Don't forget that your n's, people forget this every year. The velocity, wavelength, and the thetas are all 1s on the top, but the index of refraction is actually a 2 on the top, just because that's how they decided to set the index numbers, right? The index numbers, right? As your velocity increase, your index number goes down and so forth. All right, so anyway, I just have to solve for this now. So I'm going to multiply, I'm going to pass my sine of theta 2 up here, okay? Pass my 133 down and my 1.00029 over here. And the result is 1.00029 sine of 60. Make sure you're in degree mode, divided by 1.333. And this is equal to theta if I take the sine inverse of it. All right. And apparently you get about 40.6 as an example. As an angle, right? So if I were to draw that out, you would have a barrier here between the air and the water. The index of incidence, so I've got my velocities coming in like this, and it's always by the way, it's the angle isn't determined from the barrier itself. It's determined from the normal to the barrier, right? And then your other one is going to come out like this, so that it's going to be 40.6 degrees here. Okay. So basically you've got, this is fast and this is slow, right? And that's the way that it works, by the way. If you there are certain questions where it says, if you bend towards normal, you're moving into a slower substance. If you bend away from normal, you are moving into a faster substance. So So move into slower medium. You bend towards normal. All right, that's a pretty classic question that you would get, right? All right, so in an experiment, a block of cubic zirconia, which is kind of like just some glass, diamondy kind of stuff, is placed in water. A laser beam is passed from the water through the cubic zirconia. The angle of incidence is 50. The angle of refraction is 27. What is the index of refraction of cubic zirconia? So this is how you can actually determine the index of refraction of a certain material, right? And this is how you can actually determine if something is a diamond or something as well, right? So somebody tries to sell you something that they claim is a diamond. Well, a diamond has a specific index of refraction. So if you somehow send a laser through it and the index of refraction is off, you'd be like, sorry, this is no diamond. Okay, so anyway, basically in this one, I'm telling you that I'm giving you the sine of 50 over the sine of 27, and I would like to determine N2, and I've given you, let's see, it starts in water, so therefore N1 is water, right? N2 is the zirconia, cubic zirconia. Okay, so I'm going to go ahead and put the water index right here, but I know that one. That one's basically a given. So if you come across a question in the textbook and it's sort of dealing with some pretty common materials like water, vacuum, glass, air, and stuff like that, you can assume that those values are given. Oh, I wrote down air, by the way. I wanted water here, so I wanted a 0.333. Okay, 0.333. Solving for this, it's going to be pretty simple. It's N2 equals the sine of 50 over the sine of 27 multiplied by 1.333. And apparently you end up getting about a 2.24 as a result. All right. Here's a ray of light and approaches a jar of honey at an angle of 30 degrees. If the angle of refraction is 19.5, what is the refractive index of honey? Okay, same question more or less. It's sine of 30 over the sine of 19.5 is equal to it's going from where? Approaches a jar of honey. Apparently it's going in from the air, so I'm going to go ahead and put air here, 1.00029, and this is the index refraction of honey, okay? And so here's a few random questions that you can look at for practice. A lot of them are similar, actually. The solutions are given here, okay? You can also maybe go back up, take a look at page 452, right, for practice questions, and you can look at the sample questions in section 9.1. You'll be able to kind of get a pretty good idea of what the Snell's law is going to entail. Okay, so there it is, Snell's law.